with the log applications, you need to be pretty comfortable with an exponential equation. So my general form for an exponential equation is going to be y equals a times b to the x. X is really often the amount of time. Y is usually your total. A is your starting point, or your initial value. And B is your multiplier. Something about your multiplier, if you have a percent increase, it's going to be that 100% that you start with, plus the percent as a decimal. So what I mean by that, if I'm increasing by 10%, my multiplier would be 1.10, or just 1.1. If I have a percent decrease, it's going to be 1 minus that, the percent as a decimal. So if I'm decreasing by 10%, then my multiplier is going to be 0.9. So 1 minus 0.1 is going to be 0.9. So that's a form that you need to be pretty comfortable with in order to do the log application. So using that knowledge, we're going to work through this log application problem. This kind of covers anything you might need to know about using logs to solve these application problems. So in this particular case, we have two pieces of information. We know that at 10 minutes, there's 880 mosquitoes, and at 11 minutes, there's 836. We don't know what the initial value is because we don't know what it is at 0 minutes. So we need to find that. So the way we're going to do this is plug in what we know into that exponential form. So that 880, nope, actually I don't want to put that one on top, and I'll explain in a minute. So 836 equals, I don't know A and I don't know B, to the 11 minutes. So AB to the 11. Then I'm going to take that, pardon me, and divide by 880 equals AB to the 10th. The reason I put the higher exponent on top was so that I don't end up with a negative exponent. It just makes it easier to deal with. So what happens when I actually divide these is that the A's divide out. B to the 11th over B to the 10th is B to the 1st, or just B. And then 836 divided by 880 is 0.95. So that's my multiplier. So if my multiplier is 0.95, then what is my percent decrease? 5% decrease. So now, in order to find the initial value, that's actually a much simpler task. I can just take one of these equations, similar to how I do with a system of equations. Once I know one value, I just plug it in and find the other one. So I have 836 equals A times 0.95 to the 11th, because now I know my multiplier. So 0.95 to the 11th is going to give me a really long decimal. And then I'm going to divide by that. So without having to worry about that decimal, I'm just going to write 0.95 to the 11th. So I'm going to do 836 divided by, I can just put an answer, but I'm going to go ahead and do 0.95 to the 11th. And I get 1469.76, or about my initial value of approximately 1470 mosquitoes. So then for the very last one, I think I spelled mosquitoes wrong. Assuming the mosquitoes continue to decrease at this rate, how long will it take until there are only 50 left? So I just plug in what I know again. So I have 50 left, equals, now I know my initial value was 1470. I know my multiplier was 0.95. I don't know how long it takes to get down to 50. So, one thing you want to be careful about, do not multiply these two together. Gentlemen. Instead, you need to get the multiplier and the exponent alone first and get rid of that number. Because remember, we always do exponent first. Put the cards away. So divide by 1470. So 50 divided by 1470 gives me a long obnoxious decimal again, so 0.034 equals 0.95 to the x. And then, now that I have an exponent for my variable as an exponent, that means I'm going to use logs to solve this. So, either method when you're solving for the exponent. So I'm going to rewrite this as log base 0.95 of 0.034 equals x. So I rewrite that as log 0.034 divided by log 0.95. So I'm going to go ahead and put answer and just bring down that decimal, divided by log 0.95, and I get 65.9, or I would call that 66 minutes, because this is what we're solving for. And sorry for that amount of space. So, those are the things you may be held responsible for on your final. And that covers all of it. So